Hello everyone, welcome to codeKarle. In this video, we will be talking about how to design a social network like Facebook. The important thing to take care of here is how do we design a system that can scale up to the requirements that Facebook has. Now, I've already made a video on how do we design Twitter. Okay, so I would recommend to watch that video first because this video takes an inspiration of that video and tries to take it to the next level by making some changes which can help that system scale to a much larger volume at a lower cost and in a much scalable way. Now, the same system can be used for any other social network as well, like Instagram, LinkedIn, or even Twitter for that matter. So yeah, let's get started. Let's look at some of the functional and non-functional requirements that we want this platform to support. So from the functional side, the very first requirement is that we should be able to make a post. Okay, post is anything that we want to update on the platform, right? It could have an image, it could have a video, it could be just text, and eventually you can extend it to a lot more varieties of posts. Okay, the next thing is you should be able to like a post, you should be able to comment on a post, and you should also be able to share a post, right? For now, let's restrict it to commenting just on posts and not on comments. Okay. The next thing is adding a friend. So a person should be able to go on somebody else's profile and add them as friend. Now this is a non-directional relationship. So if I am your friend, you are also my friend. So the friendship is non-directional, but there is a concept of weightage of friendship that will come to in a while. That would be a directional concept. Okay. The next thing is user should be able to see a timeline. Now that timeline is something wherein, let's say I have 100 friends. So all the 100 friends that could have posted whatever they wanted to, I would see all of that data in my timeline. So that's the timeline functionality. The next thing is user should be able to see others post and others profile. So by others profile, we mean it's just a profile page through which you add them as friend. Others post is basically a timeline of a particular user. It could be self profile or self timeline or some particular user's timeline that can be accessed again through a UX by going onto their profile and looking at their post. The next thing is something called activity log. What this means is we should be able to log everything that a user does on this platform. So for example, if a user posts something, they like something, they comment, they share, they search for something, all of that should be tracked and should be visible to a user somewhere. Okay, so these are the functional side of things. From a non-functional standpoint, we know that any social network is a very read-heavy system. So let's say if uh, I post something, all of my friends would be seeing it, right? So for one write that is happening in the system, there are probably hundreds of reads that are happening, right? The same thing was the case with Twitter as well. Now, it should have a very fast rendering and posting time. So if I want to post something, I should get a success message that the post is saved very quickly. And whenever I'm looking at somebody's profile, my timeline, somebody's post view, all of that should also render very quickly. Okay. But some lag is okay. Now, lag and latency are two very different things. Okay. Latency should be low, but lag is okay. What lag means is if let's say a user posts something, if it takes 10-20 seconds for their friends to see that post, it's okay to have those 20 seconds in between. But whenever they see it, the page should render very quickly. Okay. The next thing is access patterns. So any social network has a very unique access pattern. So whenever a post is created, it will suddenly start to get a lot of views, lot of likes, lots of comments, and all of that. Right? There'll be a time when it reaches its peak, which will be the highest point of interaction that the post has. Then slowly over time, that post will start to decay, and maybe after a couple of days or a couple of weeks, there would be absolutely no interaction onto that post. Okay. We will use this specifically for handling images and videos because that is the heavy content, and we might be able to optimize some on cost on hardware by using this property of the access pattern. Another thing is that this platform needs to be built in a way that can be global. Now, by global, there are two, three aspects that come in. First of all, there it means that there are a huge variety of devices through which people will access it. Second thing is the platform should be available in multiple languages and should be able to handle content in multiple languages. Um, the other thing is people coming from this platform are from a wide variety of internet bandwidths. So it should not happen that it is very, very slow in some geographies. And if it is, then we need to make sure that we have enough servers in their locality, in that geography, so that people in that area are still able to access platform in a fast enough way. Okay, so global basically means that we need to have a global presence from our hardware as well. Now coming to the scale, these are some really big numbers. Facebook has 1.7 billion unique daily active users. This what this means is 1.7 billion users access Facebook onto the read path at least. Most of them, some of them could be writing as well, but most of them would be reading, right? There are 2.6 billion monthly active users. Now, honestly, I'm not sure of authenticity of this data. It could be a bit here and there, but from what I read about, these are the numbers of just Facebook and not including WhatsApp and Instagram. Those are separate. Overall, including them, the number crosses 3 billion, I believe. Okay, now these people access Facebook. 95% of these people access through mobile phones. So we need to kind of do some optimizations that are very specific to mobile devices also, because 95% user base is on mobile. So let's do some optimization for that. Okay. Now again coming to some volumes of some functional requirements. Every minute, these are the number of actions that people take. They upload 150,000 images which needs to be uploaded onto our server, spread out in various CDNs and made available for the users. They update 300,000 statuses. These are the new statuses that come into the system, which needs to be distributed across all the user base. And they post 500,000 comments every minute. Okay, so and if you look at the numbers of Twitter, they were a bit smaller than this. In fact, it's significantly smaller than this. So we were able to cache all of the data, right? In this case, because of the sheer volume of these numbers, we might not be able to cache everything. So there is where some changes we'll do from the Twitter design. So if you have not looked at that video, I would recommend to go and watch that first before moving further from this. Okay. Now, coming to one more thing, very similar to the previous video, we have categorized users into 5 segments, and we will be handling these segments of users separately in certain flows. Okay. Now, based on your requirement with your interviewer, you could make more categories or less categories, but on and off for a Facebook-like system, this should be a good enough user segregation. Now, famous users are the users who have huge number of friends. Okay. Now, in our case, I've not included followers as a functional requirement, so this would not be that big of a problem, because I believe Facebook has some restrictions on number of friends that you can have, so that will still be a finite number. But in case we start having that, uh, we would have a problem. So let's add something called a famous user as well. Now there is something called an active user. Active user is a person who has accessed Facebook in the last few days. Let's say for all practical purposes during this conversation, we'll assume that people who have accessed Facebook in last 3 days are considered active. And we'll do certain optimizations to make sure their page loads are fast enough. Okay. Live users are the users who are actually browsing through the platform right now. So instead of waiting for them to request for new posts or new content, we'll probably send them notifications through a communication between their device and our servers if a new content comes in. Okay. Passive users are the users who are not regularly active. So we'll not cache any content for them. Whenever they come into the system, we'll try to generate whatever we need to do for them. Okay. Inactive are basically the deactivated accounts. It could be fake profiles. It could be people who have requested to get their account deleted. And these are the people who do not access Facebook. We just have their accounts because it's good to have, but these are soft deleted accounts. Now let's go over the overall architecture. As usual, I have divided the overall architecture into multiple components, and we will look at them one by one. A bit of convention to start with. Things in green are the user interaction points. It could be web browsers, but for most of the users, it would be mobile applications. Things in black, these two are the load balancers plus reverse proxy plus authentication and authorization layer, which will validate the API calls coming from the outside world into our system. Things in blue are the web services that we've written. It could be web services, Kafka consumers, Spark jobs, basically the code written by us. Things in red are the databases, data stores, any clusters like Kafka cluster, Hadoop cluster, um, or any open source tool that we'll be using, or any third-party component like a CDN, for example. With that, let's start with the user flows on how does the user come into the system. Now, this is very similar to the Twitter design, so we'll try to go over it quickly. User onboarding and login and user interactions, like looking at their profile, creating their profile, updating their profile, are basically this green box, and all of that is taken care by user service. User service is the primary source of data for any user information. Okay, it provides all the APIs that the UI needs or the APIs that other systems in the overall infrastructure would need. These would generally be APIs to get a user by user ID, update a user by user ID, get details of a lot of users in bulk. So all of those APIs will be powered by this user service. Now this user service sits on top of a clustered MySQL database. Because of the volume, we might need to shard the data across multiple hardwares, but it will be a MySQL database because again, user information is a very standard and a relational set of data points. We don't really need a NoSQL database for it. Plus, one more thing about user information is it is not updated very, very frequently. So most of the information about that user, like email ID, name, location, stuff like that, is a constant information. So MySQL is a fairly good database for that. Okay. Now it also sits on top of a Redis cluster. What that Redis does is it basically caches a lot of information. Okay. So like Twitter video, we'll also be using a lot of Redis and a lot of caching here, at least for now, and we'll go over the what all is cached at what points in time. But to start with, the very first thing that stays in Redis is basically all the user information. So let's say if an API call comes in to fetch details of a user to user service, it first tries to look up in Redis. If it finds the information and it returns from there. If it doesn't find the information, then it queries MySQL database, gets the information, updates Redis, and then responds back to the user. Okay. And whenever a user logs in or user account gets created or anything happens, a event is pushed into Kafka for a lot of reasons. So for new accounts, we'll be doing a fraud check just to validate if they are not fake accounts. For any updates to the account, we might want to push that information to other systems. So let's say if the person changes their email ID or phone number, we might want to inform the notification service about their notification preferences. So all of that would be taken care of by this Kafka. Okay. The next thing is how does a user add somebody as a friend? So a user can go onto somebody else's profile and add them as a friend. Okay. All of those interactions are this green box, and it is taken care of by the graph service. Graph service, again, because it maintains the whole graph of how the network is maintained. It keeps the relationships and also the weightages of the relationships. What weightages are, we'll come to in a while, but this is basically source of truth. If you want to infer how close are two people or which user is connected to what all people, this graph service will expose APIs for all those kind of functionalities. Now again, as user service, graph service also sits on top of clustered MySQL database. Again, it will need to be sharded because it will have like multiple times data when compared to user service, but still it will again be very structured. Um, so think of it as a table with a user ID and a friend ID kind of a thing at its very core, and there'll be other tables which kind of build in other functionalities, but at the core it will just be one table with that kind of a mapping. Okay. Now again, all the user relationships would be stored in a Redis. So if I want to quickly find out that who all are the friends of a particular user, I would not want to query MySQL for all those kind of requirements because all those APIs would be used very frequently by other systems. So all that information again gets stored in a Redis cluster, which in which the key is user ID and value is basically list of friends. Okay. Now I've made one cluster. Ideally, because of the volume, I'd want to keep two different clusters for these two use cases. But we could keep one also if we can have a bigger cluster. So that depends. Okay. Now, other than this, there are a lot of other attributes that also get stored in this Redis. Uh, Key in all the places is user ID. Values are these things. So user details and friends we've looked at. It also stores what is the user type against a user ID. Remember the user type that we talked about: active user, live user, passive user, famous user. So based on some logic, user service would be able to identify what kind of a user it is, and it would be able to update that. It will get notified through somebody. So somebody would tell user service that user is now live, make it live, or user has now become famous, make him famous, something of that sort. Okay. There is something called relevance tag which we look at in the last section. But the idea of relevance tags is, so there's a lot of information that can be shown on Facebook. Let's say if I update a status about sports, instead of sending that to all of the friends, if we restrict that to only those friends who are actually interested in sports, then that will be a very engaging then that could lead to an engaging conversation between me and them. But if there are people who are totally not interested in sports and they also get to see that, they will just scroll through it, and that would not be a good experience for them because they are seeing junk content because they don't like that. Plus, it is an opportunity loss for Facebook because it could have shown something relevant which could have initiated a conversation through which some more interactions could have happened. User would have probably spent more time on Facebook, right? So relevance tags is something that will be powered through analytics. We'll get to know of relevance tags, and it will be used at the time of figuring out that who all needs to be shown a particular status or anything. All right. The next thing is last access time. It is same as the last access time that we used to keep in Twitter. It would be used for a lot of functionalities, mainly showing how much time back a user was online in chat and stuff like that. So we are not building chat as part of this video, but it could be used for that, and it could be used for some other functionalities as well. Now let's look at how does the user post some content and how do they retrieve their timeline and other user posts. Okay, first let's look at some of the generic components that we are using here. Uh, so there is a component called short URL. What this is, so let's say if somebody wants to post an external URL onto Facebook, it's generally a good idea to keep track of what kind of URLs are being posted and how are they being hit. So what we'll do is we'll have a short URL service which converts any URL into a short URL, and short URL would be posted on the platform. Okay, and then it would be redirected to the long URL when a person clicks on it. So I've made a separate video onto short URLs. You can have a look at that to know in details about how it is implemented. Okay. Now there's something called asset service. So remember, a post can contain an image and a video. Now the thing with images and videos is, so uh, people are coming onto Facebook from various kind of devices. They have a phone, they can use a laptop, and aspect ratios on both these platforms are very different, right? So if a user uploads a photo which is kind of a squarish photo, that would look very bad on a mobile phone. So we might want to do something and play with the resolutions to make the pictures look good, right? Plus, if it's a very high definition photo or a video, it wouldn't give any added advantage when you're viewing it on mobile phone. It will just add a lot more data, right? And bandwidth consumption will increase. So it does make sense to reduce the aspect ratio and the number of pixels in the content there. So all of those pieces are being taken care of by asset service. So I've made a different video on a video processing platform, something like a YouTube or a Netflix. This is basically your whole platform, which is a video serving platform, right? It takes care of file conversions to multiple formats, to multiple bandwidths, to multiple aspect ratios. It takes care of streaming the content and all of that. It also takes care of one very important thing. So remember, in the NFRs, we talked about the access pattern. So when a photo is added, in the first few weeks, it will be accessed a lot, and then it will slowly die down, right? So once the access to that photo dies down, then we don't really need to keep it on CDN. Then we can remove it from CDN so that the capacity can be used for some other photos, right? So that is also taken care by asset service, saying that which particular content would reside on CDN and which would reside on S3. So we'll be using Amazon S3 as an image store and a video store here. It also takes care of one thing like, let's say there's a celebrity who has a very old photo. Now let's say another celebrity comments on that photo. So suddenly that photo will become popular now, right? Which was a very old photo which was removed from CDNs. But now that it has become popular again, this service would keep a track of how my CDNs are being accessed, what is the hit rate on each photo, and if a photo is accessed frequently from S3, it will basically pull it from S3 and put it into all the CDNs wherever it is getting accessed from. Okay, so this is basically a video image streaming optimization to take care of the global geographical data. Okay. There's also user service and group service, which we talked about in the previous section. We'll be using it in a bunch of places. Cool. So now let's start with the user flow when they try to post a content. So that piece is being taken care by this add a post box. It talks to something called as post ingestion service. Now if it has audio video content, post ingestion service will talk to asset service. If it has URLs, it will talk to short URL service, right? And then it will have a final content that it will actually need to persist. Now for all post kind of data, I'm using a Cassandra here. Okay. Again, being a very same reason that the volume of posts are very high, right? Of the order of lots of thousands per second. So Cassandra is a good choice here because it can handle that kind of traffic on both write paths and the read paths. Now, other than Cassandra, you could have used HBase also here. Both are kind of giving similarish performances. I just chose to use Cassandra because setup for that is much easier. Okay. Now, once a particular post has come in and it got saved into Cassandra, there is a service called post service. Now, this post service is the source of truth service and the owner of this post information. And this is a service that will provide APIs to everybody else to access a particular post. Basically, if you want to do get post by ID or get a lot of posts by a lot of IDs, all of those APIs are provided by this post service. Now, whenever a post comes in, uh, post ingestion service reads a post, puts it into Cassandra, and then posts an event into a Kafka, right? And from there on, it will be spread out to further other systems, which will do their own jobs. So at that point in time, post ingestion services work is done, and then we'll get to how a post kind of comes back to the user. So there is something called analytics that you can see here. It is not a service actually. It is a lot of components. So on this Kafka, there will be a streaming consumer which will keep listening to all the events that are coming in, and it will try to tag it using a machine learning model, saying that this post is of what kind of a category. Okay. So basically, it has a classification model that is ready and it applies a post on that model and come up with some tags for that particular post, okay, which will be used to score the post on various relevance parameters. Now once this analytics cluster tags a particular post, it will put it back into Kafka from where it will be processed further. Now, doing this kind of a thing, we can do it because remember we had an NFR of the fact that some lag is okay. So if somebody adds a post, if I see it after a few seconds, that is okay. And during that few seconds, I can do all of this fancy logic to figure out who are the right set of users who should see this post. Okay. So once this analytics puts it back into Kafka, there is something called post processor which runs. Now, this post processor basically looks at the content of, so it gets the event from Kafka, which has the content of the post and some tags along with that. And obviously the user ID who posted the content. It then queries user service and group service. So these are two separate services. I've just clubbed into one box so that it's easy to kind of draw it out. So this post service will now fetch all the friends of this particular user who potentially can see this post. Okay, along with the so that is the group information. Along with that, it will also find out the relevance tag stored against the user. So we also do some user profiling that we'll look into the next section. That basically is a classification of users into some tags. So a user could be tagged to, let's say, politics and sports. Okay, and let's say if the post is also about sports, then this user would see it. If the post is about technology, let's say, and this user is tagged to politics and sports, then the user would not see that particular post. Okay. So now it fetches all of these information about a post, about all the users that this person has friends with, and tries to come up with a subset of users who should see this post. Okay. It then puts all the relevant posts into Redis. Now, what Redis here is, it basically is a timeline of all the users. Okay, so remember the Twitter video, it is something very similar to that. It basically has a timeline. So let's say user 1 posted this post, okay, and it has friends as user 2 and user 3. Okay, let's say coming after relevance, this post processor decides that only you two should be able to see that post. So what it will do is, it will, in the timeline of you two, it already has some posts. It will put that post, let's say PI. Okay, so that now when user 2 accesses their timeline, they can look up directly from Redis and they don't need to do anything else. Okay, so once we have posts into Redis, now post processor's job is done. Now coming to the other side of things. What happens when a user accesses a particular uh, uh, when a user accesses their timeline? So there are two kinds of timelines that a person can see. One is if they go to somebody else's profile and they want to see all of their posts. Okay, that is a very straightforward implementation. What that does is, it basically calls timeline service saying, I want to see all the posts of this particular user. Timeline service would then query post service saying, give me all the posts of this particular user, and it displays it back. So that's a very straightforward implementation. The other side of things is when they want to see their own timeline, which basically contains posts of all of their friends, right? Now the flow that happens is, this is the timeline box. It basically calls timeline service, which then does a lot of things. Now it gets all the basically the timeline from Redis for that particular user, right? Now again, remember the Twitter video, it would not contain all of the users. It will contain only normal users data. Why? Because normal users can be easily managed with this kind of a model. For famous users, we need to do something different. The reason is that if so right now we don't have a problem with famous user because we just have friends. But let's say we introduce a concept of followers, and famous users start having multiple millions of followers, then the problem is this post processor will have to update Redis for millions of users, and that is not scalable. So that's the reason we'll do exactly the same thing as we did for Twitter implementation. We'll basically give that responsibility to timeline service to merge the data for normal users and famous users. So what it does is, whenever a particular user's timeline needs to be shown, it queries user and group service, figures out the list of users that this person is friends with, right? And it queries the user timeline from here, which is the posts of all the regular users, normal users, and then it basically also knows the famous users that this person has friends with, right? It queries post service and asks the post service to give all the posts of the famous users, and then it aggregates the information and sends it back. Okay, now before sending it back, it could also persist this into Redis. Okay, along with a very similar implementation again, with a particular timestamp, let's say TI. Okay, it says that at TI, I have inserted this data which contains the regular users data and the famous users data. Now, the next time when a request comes in, what we'll do is we'll basically look at this timestamp. If this timestamp is in the last couple of seconds or maybe a minute, we'll return this data as it is. But if it is more than a few minutes, so we know that this was last refreshed a lot of minutes back, then what we say is we again query the posts of famous users just in case they would have posted something different. Okay, so this is how we handle the regular active users and the famous users. Now we can do a lot of optimization for the live users. What live user thing is, so when an event is posted and post processor figures out that what all friends this guy has and who all needs to get the relevant posts, it also knows, because it has queried user service, it knows that the user is now actually live. So along with sending into Redis, what it will do is it will put another event in a different topic into the Kafka saying this user is live, and this is the timeline that needs to see now. With this new additional content, somebody give him this information. Okay. Then comes the job of live user service. What this is it basically is a service which has open connections based on WebSockets with all the clients, right? So these are your regular users who are using mobile apps or web browsers who are on the platform right now. And this service has an open connection with all these users. Okay. Now, whenever this service gets a particular event saying this user's view needs to be updated, it will send the event to the app via the WebSocket protocol, and the app would then show up the new post in whatever way it needs to. Okay, so this is the separate thing that we do for live users. Now there is something called archival service, right? What it does is, so this Redis cannot contain data for a lot of period of time. What we are saying is we'll put only today's data into this Redis, right? All the posts that have come in today. For everything in the past, we'll use something called as archival service. So remember, a post can just be created at a certain timestamp, right? It can have comments, likes, and all of that, but it is made, and once it is made, right, it doesn't really, its created time doesn't really change, right? So what we can do is, and the timeline for a particular day once it is created, it just new things get added to it, but old things don't change from there, right? They remain the way they are. So what we can do is we can cache this timeline, right? But instead of using an in-memory solution like Redis, we could use a Cassandra for storing that. So what archival service does is, at some point in time during a day, it basically fetches all the users' timelines, whatever have been created. It puts it into something called a aggregated timeline Cassandra and clears this cache. Okay, now this makes sure that we have a finite amount of data within Redis, which is small. Okay, it's not a lot of data. Now for the users where this doesn't exist, it will try to create that kind of a timeline by simulating the same behavior. It can in fact call timeline service and get the timeline and save it for all of those users. Now the format in which it will save is roughly similar to this. What it will do is it will say that user UI at a date DTI has a timeline of a particular thing, right? Now, coming to timeline service, an actual timeline needs to be created. It will not only query from Redis and post service, it will also query from archival service if the user scrolls down a lot and needs to see yesterday's data or day before yesterday's data. Now, all of the older data need not be computed at that point. At that point in time, it can just be looked up from this itself. And this can store data not only for the active users, but also for famous users, passive users, and all of them. And that's the reason I wanted to use a Cassandra here, because now we can scale this also infinitely, right? And wherever we are saying we are caching something, we are storing something, we are just storing the post IDs. Okay, we are not storing the actual content. And to get the actual content, this post service can be used to construct the whole payload. Now there is one more thing with this. At places where we have used Cassandra, there is a potential problem that could be created. We could create hotspots. What a hotspot is basically, so Cassandra is basically a distributed thing which is across a lot of machines, right? Now, if we don't choose a partition key properly, it could potentially happen that only one machine is serving most of the live traffic. All the updates are happening on one machine, and all the reads are happening from the same machine, and all the other machines are just lying idle with no work. This could happen if you have a partition key, something like a date range. So all the updates of today would happen on the partition which is handling today's data, and all the reads will also happen from that, right? So we need to be a bit careful about choosing the partition keys there. A user ID based key would be a fairly good thing, but a date based thing would definitely create hotspots. So wherever you are using Cassandra, we need to be very doubly sure of, basically to make sure that we don't create a hotspot. Okay, coming to the last section of this video, let's talk about how are likes and comments handled. So assuming there's a UI through which people can do a comment or a like, this could come through various devices like phones, browsers, whatever, right? So whenever a user presses a like button, the request goes to this like service. Now this like service is our owner of all the like information. So even when you want to make a like put a like, or you want to get the number of likes in particular post, all of those are powered by this like service. Okay. Now, whenever a person adds a like, that information gets stored into Cassandra. Think of it as a table saying user ID and post ID. Okay. So post ID contains the post which is being liked, and user ID is basically the user who's liking it. Now, let's say if you want to add a functionality of like being put on a comment, right? Then comment would also have an ID. So we can add a parent type kind of a thing or post type kind of a thing saying post ID so and so, and post type could be either a post or a comment or anything, right? And then the user who's liked it. Alternatively, if you want to add more types of likes, like upward, downward, or something of that sort, you could add a like type also in that. Cool. So that becomes the permanent store. But there's a Redis also that is used here. What is that for? So generally what we see is whenever a post is displayed, along with the post content, the number of likes are also shown. Details are not shown, but number of likes are shown, right? So the number of likes is being powered by Redis. Redis stores information of the count of likes on a particular post only for the recent posts. Okay, once the post becomes outdated, this particular entry will have some TTL of a few days and that will get expired. But for all the recent posts, it should have a information of the count. So whenever a like comes into the system, it gets stored into Cassandra and Redis update gets called. So basically there's a thing called update and get in Redis, which does the atomic update into Redis. So that takes care of thread safety and all of those issues. So that can be used to like power the updates. Cool. Now once a like has been posted, that information would also be put into Kafka, saying this user has liked this particular post. How that will be used will come to in a while. Now let's get to comments. So again, there's something called comment service, which is basically the repository of all the comments into the system. Whether you want to like make a comment or you want to get all the comments from a post, that will be powered by this service. And this uses a Cassandra as a data store. A very simple schema it'll have a post ID and a comment text, and whenever you want to get all the comments on a particular post, you just run a where clause on the post ID. It'll obviously have user ID and all of those attributes as well, timestamp and all those things, but those are minor things, right? Now whenever somebody wants to get all the comments, that is also powered by this Cassandra. We don't really need a caching here. So this Redis was used because it was storing aggregate information. So instead of Redis call, the alternate was to do a select count star query from Cassandra. But over here, in case of comments, it is anyway lookup by ID, whether it is on Redis or whether it's on Cassandra, it's not too slow. So we can use Cassandra without any cache. Cool. Now we did not talk about sharing of posts earlier, but sharing of posts would exactly be implemented in a way a post is implemented. So a shared post would be just another post with a parent ID of the original post so that it can be referenced that from where is this post coming from. Okay. Now whenever a comment is added, it also gets posted into Kafka for further analytics. Now let's come to something called activity tracker. So you remember we talked about when we talked about functional requirements that we want to capture all the activity done by a person on Facebook, right? So let's say a person makes a post or a person likes a post, all of that should be tracked. So anyway, all that information is coming into this Kafka, whether it is a person liking something, whether it is a comment, whether it's a post, everything is actually coming here, right? All we need to do is to store that information against a user ID with a timestamp that this was the action taken and some attributes of that action. So this Cassandra of activity tracker would primarily have a user ID, a timestamp, action, like action could be liked a comment ID or made a post with a post ID or searched with a search string, all of that, right? So all of that would be powered by this activity tracker. This would have both insert APIs into Cassandra and get APIs in, to fetch the data from Cassandra and show it onto an activity UI. This activity tracker would listen to the same topics that everybody is writing to. Okay, now coming to search. Search is implemented in exactly the same way as it was in Twitter. So I'll not go over it in much detail, but assume that if all the events are anyway coming to a Kafka, there'll be a search consumer that reads all those events, stores it into an Elasticsearch database, which is very efficient for text-based searching. And there's a search service that sits on top of that Elasticsearch, runs a query, and returns the data. And in some cases, we might want to cache the results of the search response. So before sending it to the user, we might cache it in a Redis as well. All of that is abstracted as part of this search box, for which you can look at the Twitter video in which I've explained it in much detail. Cool. And while a person is searching, that information also gets pushed into Kafka, so that can be logged by activity tracker. Okay, so we had put a lot of information into Kafka, saying that we'll do some analytics on it. Let's try to take some examples of what kind of analytics can be done. So let's say a person posts a content, right? That content can be classified using some very standard classification ML algorithms into certain tags. So, for example, a post could be tagged as a sports-related post, right? Now, if a person is having a lot of sports-related posts, that means the person is giving us a signal that that person is interested into sports, right? So what we'll actually do is we'll have this Spark streaming consumer running, which will put all the information about all the activities done by a user into this Hadoop cluster. That would include the posts, the comments, the likes, whatnot, right? And then we'll have some algorithms which basically do this user profiling, saying if a user is liking a lot of sports related posts, that means the person is interested in that. If the person is commenting on similar posts, that also gives the same signal, right? So all of those information could be used to generate a user profile which classifies users' interests. Now in real Facebook, we have the option to explicitly like a particular thing, right? Let's say I like a sports page, that means I'm explicitly giving a signal. But in case of this scenario, we did not include it as part of functional requirements, so we can use this data to infer all of those things, right? So that basically creates a user profile. Once the user profile is created, that is put back into Kafka. And remember the very first section where we had a user service which was storing a user profile tag kind of a thing. User service basically reads that event and stores those tags against a user, which is then used for various kind of things in the system that we talked about in the section 2. Okay. Now there is something called graph weight. So what is that? So let's say myself and Elon Musk are friends on Facebook, hypothetically. Okay. Now I might like a lot of his posts, but he might not really like mine, right? What that tells is I like the content that he posts, but he does not like the content that I post, right? So even though we are friends, even though we'll be shown some of the content that both of us might post, but there is some affinity of mine towards seeing his post rather than somebody else's, right? That information can be captured by the graph weight job, which basically says that out of all my friends, whose posts have I liked most or whose posts have I commented the most on? And basis that logic, it will create a profile of mine saying I am most inclined towards these two, three people and less inclined towards the rest of them. So I'll see more posts of these people, right? That becomes your graph weight job. Now this runs on top of a Spark cluster which can query the data within Hadoop, run a couple of Spark jobs, do all the maths, and publish data, right? Now we have left something called trends. Trends is basically something very similar to the trending thing on Twitter. We talked about that while during the Twitter video. It basically tells us what people on Facebook are talking about right now. Basically, what this streaming job will do is basically it will take all the posts, all the comments, tokenize them and split them by space characters, remove some very common stop words like a, and, of, the, for, is, and all of that. And then the remaining words will be put into this trend service, tagged rank by their count. So at any point in time, we'll know what word is the most used word right now, right? And that will give us some inferences about what kind of things people are talking about. And it cannot just be words, it can be phrases also. And we can build in a lot of intelligence to figure out what people are talking about and what people are interested in right now. And all of that information could be stored in a Redis cache because anyway, it's a temporary information for right now and it will get updated in a while. And there can be a UI kind of a thing that can be built on top of it if there's a need. Cool. So these were the functional requirements. Now coming a bit on the non-functional requirements. All of this is fine that we have talked about. One thing that I did not explicitly mention, but all the services that you see here and in the previous sections were scalable horizontally. So whenever traffic increases, you basically add nodes into that particular service or that particular database or that particular cache, and it would scale automatically. Okay. But that being said, we still need to, there are a lot of different kind of technologies used here, and we need to do a lot of alerting monitoring on all of these things, right? So for example, if there's a web service that we have built, we need to measure the latencies that it is having, the throughputs that it is having, the CPU and memory usage within that, the disk usage, and then if anything kind of spikes up, then we need to send out an alert. Similarly, for all the databases, we need to keep a track on what are the throughputs and latencies again, how many queries are getting executed, what is the disk space. We don't want a database disk to be full at any cost. So again, CPU memory is anyway there. So all of those things on the database, on the caches, on the web servers, on Kafka, all of those things need to be monitored on. And as soon as they go beyond a particular threshold, there needs to be some good enough alerting so that the people get to know that something is going beyond limits and can look into it proactively, so that to make sure that we are able to maintain the uptime and latencies and everything, thereby maintaining the non-functional requirements. Cool. So I think that should be it for a Facebook kind of a system. Now, just to reiterate, the same design can be used for any other social network like Instagram, Twitter, LinkedIn, or anything of that sort. Thanks for watching this video. If you have any suggestions on what videos we should make next or how we could improve this one, do let us know by commenting here. And don't forget to subscribe to this channel and share the videos with your friends while we keep bringing you more such content. Happy learning!